Okay, let's see if I can explain how to do a half-life problem. So when we're talking about absolute age dating, what we're saying is if a rock contains the appropriate minerals, and if those minerals contain the appropriate atoms, we can use how those atoms decay or break down over time to determine how old the rock is. So we need a specific mineral to be in the rock, and it has to be one that we typically call it's radioactive, but it just suggests that it's unstable at its current configuration. And so what it's going to do is over time it's going to change into something else. So we call the initial atom that is unstable the parent, and we call the stable version the daughter. And so it's not particularly important that you understand all the ways in which an unstable element can change to a stable element, but what we want you to be able to understand is the idea of what's called a half-life. So the half-life is the time it takes for half of whatever you started with in that initial mineral to change into the stable version, whatever that is. Now there's a variety of different atoms that change into other stable atoms. So uranium, most people have heard of, is radioactive, meaning it's unstable in a certain form, and that form will eventually decay or change to lead. So a uranium lead is a system that we can use to figure out the age of certain rocks. There's potassium argon. There's another set of atoms where we have potassium, which is unstable in certain forms, and over time it decays or changes into argon. And what we can determine is the time it takes for half of whatever you start with to decay from unstable to stable. So when you're given an example, and the idea would be that, let's say we went out in the field, we grabbed a sample, a rock sample, that we determined had the right mineralogy, hadn't been altered or changed. We take that back to the lab. Now, it is a rock that has existed for a while. So when I go in and I find that mineral and I extract it and powder it and put it through a machine, that machine can actually count the number of atoms that are there. And it's going to count both my unstable atoms that are left and the stable atoms that have formed from the decay of the unstable atoms. So if we were to do that, so let's say we grabbed a sample, we found it, we brought it to the lab, and we identified that it had these two atoms here. And this is the unstable, this is the stable version. And we know from past experiments that it takes 400 million years for the half-life to happen for this particular system. What that means is, kind of what we just said, is it takes 400 million years for half of whatever I have of the parent to change into the daughter atom, which is the stable atom. So of course, when I run it through my machine, I might get a count like this. Now look, these numbers are just made up. They're super small. There'd be super high amounts because they're super tiny. But that's not the point. The point is we can use whatever numbers we want. You just understand the process. So if we were to evaluate my mineral, and this is what I got in my little machine that told me the count. Now this is not what it was when it first started. This is the count today, and we know that the number of parent and daughters has been changing over time as there's been decay happening. But there is something we have to remember, and that is that in order for the absolute age system to work, we have to know that at the very beginning, when this mineral first crystallized, this is why igneous rocks are the best source, when they first crystallized, that only the parent atom got locked into the structure of the mineral. There was zero daughter product. That has to be true for this to work. And this is really the starting point for you. So what does that mean to you? It means that every daughter atom that you see today did not exist when it was first born. So where did these come from? They came from the decay of the parent. So I can figure out how many atoms of the unstable, the parent version, that I had at start, because I'm just going to take this number and add it to this number. And that would mean that when this rock first cooled and crystallized and the mineral in it, it had 200 parent atoms and 0 daughter atoms. That has to be true in order for this to work. So whenever you're given a problem of a number of parent and daughter, you know that in order to start the work on the problem, this has to be true. So you just take all of the daughters and you add it back to the parent, and that is your starting point. So what do we do from there? We just say, look, we're going to say that a half-life is defined by the time it takes for half of the parent to decay. So all you're going to do is take half of this original value, write it down here. Where did that half go? Well, it converted into daughter atoms. So, and how long did that take? Well, by definition, it took 400 million years for this particular system. The other systems will have different half-lives, so it would take a different number of years. But this particular one, and this particular equation, or at least question, says that it took 400 million years for half of the original parent to decay to 1,000 here. So, but look, if I look at what I've calculated today, that does not match the ratio after 400 years. It's too high. So what that means is I need to keep taking half. And that's really what you're going to do. You're going to keep taking half until this number matches the number that you have today. And so for this example, we take another half, and we have 500. Where did that 500 go? Well, it turned into daughter, and I already had 1,000, so I'm just going to add it to there. This is my ratio that I have after how long? Well, another 400 million years. So it does match what I have today, so I'm done. I can stop. How old is my rock? Well, in order for it to get to this ratio, I needed 1 half-life, 2 half-lives, and each half-life is 400 million, so I can just multiply 2 times that, or add, right, 400 and 400. So the age of my rock is 800. Now, if this value that I measured wasn't 500, it was less than, you would just continue to take half, keeping track of how many half-lives, until the number here matches the number there. As soon as it matches, you stop, and you count up how many half-lives. That's the age of the rock. So I'm never going to give you an example where it's in between. We're just doing some basic stuff, giving you the idea of what it's like to figure out a half-life. So whatever value you're given to begin with, you're taking the daughter, adding it back into the parent, and that is your starting point. And then you just continue to take half each time, keeping an eye on the original that was given in the problem. Once it matches, count how many times you had to take half. In this case, it was 1, 2. So 2 times 4 is 8. It's 8 million. If it took us 5 times, we would multiply 400 by 5, and that would be our age. And so that's how you're going to go about working the homework problem, at least the first question in the homework problem. Hopefully that's helpful, but if you still have questions, you can certainly reach out to me.